Okay, in our last session, we explained about the dual connectivity issues where you have your 5G UE connect with your macro cell and also the small cell simultaneously to improve the data rate. So that's probably the architecture, the major architecture in this 5G network. Okay, so the next thing is the 5G measurement penetration loss in higher frequency. Because as we mentioned before, there is a lack of frequencies in wireless communications. So as a result, people have been looking for higher frequency bands for transmission. So we'll be going higher and higher, and the the issue with higher frequency is that it may not be able to transmit efficiently due to the penetration loss. In other words, the loss is higher in that case. So if we try to take a look at this penetration loss, there is a frequency and this is the penetration loss. We see that as the frequency goes higher and higher, the loss seems to be higher and higher. And it differs in different scenarios. For example, this standard glass or IRR, infrared resistant glasses. So if it goes through a IR, infrared resistant glass, then you encounter more losses. And as we can imagine that IRR gas is sort of prevent the EM wave from traveling. So it eliminates part of the signal and it give you losses. And then residential building with reasonable loss here, and campus building and dining room, so on and so forth. So you see that loss goes up with higher frequencies. Therefore, uh, in 5G, we have this multiple antenna architecture, and it will be the case where uh, we're going to have more detailed discussions on this multiple antenna architecture. And as by intuition, as you can imagine, if we go up frequency, we get more losses. As a result, we use multiple antenna systems at the transmitter side and also at the receiver side, so as we can enhance or improve the signal. And also it increases the data rate also, because if you see the streams here, you have multiple streams. The first stream, second, third, so on and so forth goes up to NS. And it goes to the digital recording and then goes to the transmit antenna and then it goes out. And the other thing is the analog beamforming. When in the analog beamformer, the streams comes in and then the analog beamformer does the amplitude and phase shift. Normally, people would do phase shift in most cases, but in some cases, people do amplitude also. So uh, that also tunes the signal before it gets transmitted. And then there is a hybrid version of it. In the hybrid version, the digital recording in front and then analog recorder here. So it goes here and goes here and then gets transmitted. And then waveforms for 5G and its pros and cons. There is all QAM, and QAM and also OFDM, FDMA, and with various waveforms in this 5G framework. And it has uh, each one has their pros and cons, advantages and disadvantages. So you have, for example, for the first one, for the first one, you have high SE, high SE, and then uh, no out of band. Out of band meaning in some signals its spectral shape is not very regular and it transmits outside of its band. That's interference to other people. So we would try to prevent this OOB out of band interference. So if it has low out of band, then we will consider that to be an advantage. So we like things to have low OOB, and also it's robust in asynchronous as access. And its cons is that it's not MIMO or FDM compatible, and it's delayed for short bursts. And the regular QAM is sub-band-wise configurability, and it allows asynchronous FDMA access. And it has, but the cons is that it has degradation due to orthogonality in some cases. When the things are not orthogonal, we have trouble that uh, kind of uh, get us into trouble. What kind of trouble? Because it's not orthogonal, the signal at the receiver side will interfere with each other. And this OFDM is robust to spectral and temporal offset. And the cons is that it's possible degradation due to time localization constraints. FCOFDM is coexistence of different waveforms in the same band, and not all features of each multiplex waveform candidates can be maintained. And this ZT-OFDM has low PAPR. PAPR is peak to average ratio. We like things to have low PAPR. The reason is that PAPR, when it's high, it gives us problems in which uh, the, the amplifier goes into the nonlinear region. You know, the issue being that your peak is very high with respect to average signal strength. That's high PAPR. But when you have low PAPR, your peak signal peak is not very large with respect to the average value. As a result, low PAPR gets us easier in terms of circuit implementation. So that PAPR is an important factor, and the issue is severe in OFDM systems. That's why we like things to have low PAPR. That's the advantage of this OFDM, but the disadvantage is that it's susceptible to temporal and spectral offsets. And this FDMA also has low PAPR and low SE, and BQAM has low PAPR, but it has low MIMO compatibility. Because MIMO, while using multiple antenna, it's very easy that those antenna signals get interfere with each other. So that's a MIMO issue. And also this OFDM subband-wise configurability coexistent with CP OFDM is ISI in certain conditions with large delay spread. and subband-wise configurability, and it coexisting with CPRP and its ISI in certain conditions with large delay spread. Okay, so now here we come to uh, the 5G use cases. So we have this enhanced mobile broadband. Uh, enhanced while in this enhanced mobile broadband, uh, uh, it's gigabytes in a second. This is called the EMBB. EMBB, the previous mentioned EMBB. It has gigabytes in it. So what does it do for us? For example, you want to download a movie, a book, or anything with large volume, it can be done in a few seconds. Right? A movie is like 5 gigabytes or something like that, and you get high quality videos in a second or a few seconds. And then it's smart home and built-in applications. So for example, the IoT connects your refrigerator, your air conditioner, your lights, your doors, your cooking, everything can get connected and it automatically starts itself with remote control wirelessly. That enables a smart home. And of course, the most simple one that is the voice, speech and voice. And smart city, for example, emergency rescue and traffic lights, uh, the home, the video surveillance, every kind, all kinds of application in the city. Of course, then there are discussions about um, the confidentiality issue. Some people are concerned about whether or not such application can violate your privacy, human rights issue, because it's recording all the time everywhere in the city, and there are legal and ethical discussions about this. And then 3D video, UHD screens. And then the next thing is work and play in the cloud. For example, video games, augmented augmented reality. The reality is to do the AR, the AR stuff, and industrial automation, and then mission critical application, for example, e-health, and then another key application is self-driving car, self-driving. So some cars, automatic self-driving, that has been under development for quite a while and going to be realized in the next few years. Self-driving. Okay, so here is enhanced mobile broadband and then machine type communications and ultra reliable and low latency communications. So it wants us to do reliable and low latency applications. So that's sort of a future, prospect for 5G and future wireless communications. So let's do a brief summary. There is a widespread belief that millimeter wave, wave band will provide large bandwidth. Yeah, and the reason is we have been running out of bandwidth frequencies in the low band. and as a result, we want to go higher. And then network densification is a key part of the techniques needed to meet 5G capacity. And of course, that the reason is that uh, 5G, um, the network densification enables a lot of things. First thing is we have done a tutorial about the frequency reuse, right? Frequency reuse. So when the network is dense, reuse factor is going to be better. So that's a network densification, and it's a key part of the techniques needed to meet 5G. We need to reuse it, and the other aspect is that when the network is dense, we get better chances of accommodating more users. You can imagine this if uh, uh, if a network a cell accommodates 100 per people, you want the cell to be small. When it's small, uh, each cell still accommodates 100 people. Then when it gets smaller and smaller, then you can accommodate a lot more people within a small area, right? Because let's say an area contains 10 cells, now it contains 100 cells, then you're going to accommodate 10 times more people than it used to be. So that's sort of a densification. And then 5G will use active antenna arrays. The arrangement of the antenna in the 2D array and the vertical horizontal dimension will depend on the angle spreads in azimuth and elevation. So this is kind of the beamformer. If we go back a little bit and see this, well, those analog beamformer is doing is he's trying to do the phase shift and also the amplitude so that combined together it forms a beam. The multiple antenna can forms a beam and the beam will combine with each other and then point to a direction. For example, they all steer their gains up to this point, then it would steer the game up to this point or another direction depending on where the receiver is. So this is kind of the beamforming architecture. No, the active antenna array, the Angelman antenna array, and then it will enable the azimuth and elevation direction beamformer. And beamforming architectures that perform both analog and digital signal processing also need to have some of their parameters aligned with the environment and system. And having a good channel model is fundamental to any study of the physical layer. So having a channel model to the physical channel. So in the old times, we have a measurement for many channel models, but those channel models may not be applicable in terms of the millimeter wave or higher frequency band. The reason being that when the frequency goes higher, the behavior of the channel changes. So it kind of give you uh, gives you a issue when you have this uh, channel changes in the high frequency. And it will enable various applications. For example, we mentioned this automatic driving, IoT, multimedia. For example, you want to watch video, but let's not forget that a person watching video is easy because the rate is sufficient. But imagine 100 people watching, 1,000 people watching. How many data rate do we need for that application? It's huge, tremendous amount. So that's a challenge. And also remote healthcare, for example, doctors will be able to diagnose patient remotely. Okay, so that's the IoT uh, multimedia and healthcare. Okay, so now let's go one step further to this hybrid precoder design to large-scale MIMO. As we mentioned in the previous slide, we have uh, we have this multiple antenna system. We need to perform MIMO system, and we also like to perform uh, multiple streams transmission at the same time. Not only that, we want also to do beamformer. So here is in this session we are going to uh, go through some design techniques. So the motivation of hybrid beamformer, if we compare 4G and 5G up to 5G, originally we have 10 millisecond latency. Now 5G we are demanding less than 1 millisecond. And as we can imagine, we are expecting 7.2 exabytes per month. Now we are expecting 50, which is a lot, and that is going to happen in 2021. And peak data rate is 1 giga. Now we are expecting 20 giga. So we are expecting things to get higher and higher. And then the available bandwidth is uh, available bandwidth is 3 giga. Now we like it to have 30. So that's also part of the reason. When we are expecting 30, then what can we do? Not much we can do. We just go higher frequency. Right? That's kind of the thing we need to go. And then 100,000 connections per km square. Now we are expecting a million. How come? We don't have that many people in a km square, right? The issue is that um, when we are talking a million people, when we are talking a million, we're not actually talking a million. We are uh, talking about a million devices, probably more devices than people. So that's a paradigm shift in the future. You're going to see more devices connected. Then of course, then there will be privacy issues also. You have these cameras, videos, speech recorders around everywhere, and you need that connection. Um, you need a connection to be secure and to maintain privacy, to maintain its authenticity. And beamformer technology is one of the promising ways to attain the requirement of 5G. A hybrid beamforming is a shootable architecture which can exploit large mmWave antenna array with reduced architecture. So here is the types of hybrid beamformer. The first thing is the fully connected architecture. Uh, you have this RF transmitters that comes in, and those transmitters, they uh, the data streams coming in and then gets this analog recorded phase shifted and then goes to the antenna, gets transmitted. And then the other thing is the NRF phase shifter, partially connected. What that means is when you have things coming in, each stream is connected to some of the data, some of the antennas, not every. Here, every stream is connected to every antenna. Now here, it's connected only part of it. So if we look at the precoded matrix, it's going to be diagonal. And then also there is a dynamic subarray architecture. You have NRF phase shifters. So you have beamformers coming in, and then RF, you have NRF RF chains, and the switching method does a switch, and then it goes to phase shift and then gets transmitted. Okay, so here is the spectral efficiency, and as you can always imagine that when uh, when an array is fully connected, let's go back a little bit. When it's fully connected, you get a lot more freedom than this partially connected, right? So you are going to expect better performance for this fully connected. But also, um, partially connected has the advantage of simplicity. It's more simple. It's simpler than this. As you can see, the matrix is diagonal and simpler. Okay, so um, so let's continue on. Then, so if we do the simulation doing this spectral efficiency versus SNR, you see this uh, fully connected ones, fully connected ones perform better than partially connected here. This, for example, this yellow, purple, they're partially connected. Uh, the blue and black, the dark color is the fully connected, performing better than others. Okay, so let's see what's going on in this MIMO architecture. You have inputs that goes in, and the input usually refers to serial to parallel. Input refers to serial to parallel uh, conversion. So that, for example, you have 8 antennas, 16, 32, and people have been talking about hundreds of antennas because of the reason that I mentioned. We want to have higher density and higher data rate. So, uh, but let's just say you have M antennas, and in this case, you have M antennas, and it goes to the receiver side. The receiver gets the information. It's trying to do the detection, and when it does the detection, then at the end, there is a block for parallel to serial conversion, and then gets the output out. And the signal model is y is equal to hx plus v, which is a non-channel matrix, and n larger than m. The elements of X belong to a finite alpha size S. So for example, if you're using QAM, then what's going on here? You have 4, right? If you use BPSK, what's going on here? You have 2. You have size 2, right? This is BPSK. You have plus 1, minus 1 as the signal set. As a result, the set of the signal is equal to 2. And if you have 4 PSK, then you have 1 plus J, 1 minus J, so on and so forth, plus, minus 1 plus, minus J. You have 4 combinations, and you have 4. You have 4. So if we take a look at the signal model, at the receiver side, Y is H multiplied by X. You look backward. and you see what's going on in here. And that V is the noise. That is the noise. Okay. And the most common detector is the maximum likelihood detector. The maximum likelihood detector goes like this. You have XML equal to argument that minimizes y minus hx to the 2 to a degree 2. And people would often conduct QR decomposition of h, and then h equal to qr, where q is equal to this and orthogonal. So q is equal to I and r is this. This is upper triangular. So this QR decomposition, if not familiar, I would recommend to check out linear algebra, the numerical linear algebra. There are various approach that performs this decomposition. So the original argument about y minus hx, y minus hs square, that will be equal to qh, because of what? Because qhq is equal to I, and then multiply y minus hx to the square 2 plus I minus qq. And then you do some conversion, you go down to here, you have qhy minus rx to the square plus I minus qhy square. But I want to bring it up to you that when you are minimizing this, that will be equivalent to minimize this whole thing. But this whole thing, this whole equation is no more than just minimize this. How come? Because I minus qq, y are all known. I is the identity. Q, after you do the decomposition, you know q. Y is the measurement. Y here is the measurement. So as a result, there is no variable in this part. No variable. The only thing you need to do is you just do the square. So the equivalent problem will be to minimize this one. So equivalent problem to minimize y prime minus x, where y is equal to what? Y prime is equal to this, qhy, y prime minus x to the square. Then we can do a tree representation. The tree representation is calculate. This, it can be broken into this part. So if you look at this y with this upper triangular, and this is a variable to be solved, then the problem is this minus this times this, and this minus this times this, and so on and so forth. So you get this equation. And this equation is to look from bottom to top. And then you have y minus this, and where this minimize f1 xm plus f2 xm minus 1, so on and so forth. So if we look from here, x minus 1, you look sequentially, what do you get? You get f1 xm plus f2 xm minus 1 xm. So you look for xm first, and then look for xm minus 1, and then look for x minus 3 minus 2, so on and so forth, sequentially. As a result, for example, you have a 4 by 4 MIMO system with BPSK. So this is a root node. So you look for x4 first. x4 equal to minus 1 plus 1, then it goes down the tree. And then you look for x3, you look for x2, you look for x1, you go all the way down to the bottom. And at the bottom, then you get this maximum likelihood metric. As a result, you get ML solution. So if we go from the beginning all the way to the reformulation, the vector form and down to the tree structure, and we get this tree. So as a result here, what we are showing is we actually have a maximum likelihood detector being turned into a tree search problem. So that's the how MIMO system work. Okay, so let's finish this a little bit of the MIMO transceiver architecture and then move back to the discussion for this 5G framework. So what we just did is to look into the details of the how MIMO architecture is working. So that's kind of a sort of a mathematical detail, and I believe from time to time you're going to encounter the, the transmitter, some of the transmitter receiver design issues in along the way of your career. Okay, so yeah, so let's come see this. Uh, so 5G, in summary, 5G will be a very different framework. Will be a very different. In that it accommodates a lot of applications, a lot of users, high data rate, high population density, and device and density, not even human communication, including uh, device communications. So there is an NGMN white paper describing the demand for the 5G with details. And 5G vision defined around business context and characterization based on use cases based models. So you will see we have broadband access in dense areas, broadband access everywhere, trying to accommodate high speed, low speed, indoor, outdoor device and human, and high user mobility, for example, this high speed chain and massive Internet of Things, extreme real time application communications, for example, low latency, and live night communications. For example, in a disaster scenario, you want to kind of get into the rescue very fast, and this is ultra reliable communication, and this is broadcast like service. Okay, okay. These key scenarios to be addressed throughout the multiple stages of 5G mission critical service, uh, fully reliable, high availability. For example, let's assume that let's imagine if an earthquake happens, then the power is down. The the power is down and the landline connection may be down. Then what will you be able to do? You use wireless communication, right? And then when the power is down, is 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 down, then you need to use uh, sustainable power, sustainability, right? Sustain the power with itself, battery, uh, engine starter, things like that. Is except you will not be able to use the, the regular power. Okay, so that's the reliability, availability, and also coverage scalability. A massive IoT connectivity uh, for a new wave of device types, high density deployments, as you can imagine. How many devices are around a person nowadays? It's like tens, 100, right? So those devices need to connect to automate smart applications and robust QoE quality of experience, new revenue opportunities. That brings up new revenue opportunities for the service provider, and also fixed broadband and mobile broadband. So you imagine you have a city with various smart applications, surveillance, and different contexts of the same environment. So you have 10 times the bandwidth per connection, low MS latency, and finite reliability, meaning 99.999 reliable, and 100% coverage. That's more than 10 times connection and 50 megabits per second per connection, 1,000 bandwidth area, and 10-year battery life, reduction in TCO, and also enhanced mobile broadband, connected vehicles, AR, VR, augmented reality, virtual reality, 3D view, ultra high definition video, haptics sensing, massive IoT, remote machine control to automate a lot of things that serves our lives better. Mission critical services, fixed wireless access, and customer segments, consumer, auto industry, health, and industry 4.0. Even nowadays in the factory, you can imagine a lot of devices, right? Machines working in the industry. But once they are connected, they automate themselves. And agriculture, smart city, public sector, smart building, utilities, education, and transport, and B2C, B2B, and B2B2C business model. Okay, and if you see this figure, it will be the vision to look in the future. You see user experience, data rate, traffic capacity per area. Now we are not only talking per connection, we are talking about per area. That pushes the design one step further into consideration of the geographic area and energy efficiency and connection density, latency, mobility, spectrum efficiency. All those things need to be connected, need to be considered. And enablers, meaning the technologies to enable this. So we now need wave, wave, millimeter wave, error correction code, and then network slicing. And then massive MIMO, as we mentioned a few slides before, we put a lot of antennas, hundreds, even thousands in some cases. But it's on the experimental stage, not yet commercialized. And then massive connectivity and low latency. So new for 5G, the RAN architecture is new air interface, CPO-FDM, massive MIMO, mmWave, beamforming, shortened TTI, flexibility in band sizing, so on and so forth. So that's uh, the device, and also at the device level, at the connection level, and at the application level, we look at this thing in every aspect of the design. Okay, and here is the D2D V2X, meaning you have device to device. So now not only people, human beings communicate with human beings, with development of AI, machines need to communicate with each other for the data, right? So device to device communications, and they automate themselves. For example, a thermometer will communicate with air conditioner, and if the temperature is too high, then the air conditioner is started automatically. And then vehicle to everything. For example, vehicle to roadside unit, or vehicle to human beings. Devices connected directly with no network. And also the topology flexibility. Topology needs to be flexible uh, so that it can accommodate different scenarios. And meeting the goals, you have those uh, low latency connections, data rate requirements, and you have these technical requirements, and then significant network investments. So you need to achieve those requirements depending on operator deploying cells and resiliency. And pain points for commercial slicing. So the problem is that uh, it needs a very sophisticated design in terms of the RAN orchestration. For example, we mentioned about the dual connection. While the dual connection comes in, how do you synchronize those small cell and macro cell? It needs some kind of orchestration. Right? And the synchronization gets more complicated. And with the evolution, 2G, 3G, 4G, up to all the way to 5G, some of the applications and legacy needs to be accommodated, right? Accommodated. This is called backward compatible. Okay, so an example of secondary implications. So, for example, this car and this car, they are roaming on the road, and they use different providers, different vendors, different applications. You kind of need it to be able to communicate and accommodate the technical spec with respect to each other. Okay. And also 5G, 4G compatibility. Okay. This is a bit hard because people have invested a lot in the old generation, for example, 3G and 4G. And now we have a new thing, 5G. Kind of how to phase this thing out and bring this in. It needs a commercialization process. Okay, so this is CN architectures. Traditionally, 3GPP has documented the architecture of the system using reference point and network functions. Uh, but nowadays, um, people uh, still looking at 3GPP, but 3GPP is moving very fast. Moving very fast. It requires huge investments from the providers. Okay, and then the CN we define as a service-based architecture, and functions, services, and operations. So each entity in the architecture is called a network function. We'll skip some of the uh, technical description. Then operators and alliances, as you see a lot of operators and alliances in the area. So where does that take us? Devices communicate with the app and web with APIs, and those APIs communicate with the core and then communicates with the MEC, both going through the network using those standardized API. So to conclude this, to conclude this, uh, we need to adopt new form of HTTP for web and APIs, and 3GPP are in the process of defining the interfaces with SPA architecture. So there's an opportunity to work with telecom ecosystems. And URLLC and massive IoT are the target use cases for 5G. And B2B, B2B2C business models drive 5G business case. Of course, it's always the case that every technology either succeed or fail, and it really depends on eventually the commercialization process. It's not like we can call it, we can get a definite answer for that, but eventually commercialization is the key to decide whether it succeed or fail. Okay, I think that would be the end of my lecture. That would be the end of this introduction to 4G and 5G network. And I'd like to thank you for your attendance, and please look through the slides, and if anything is not familiar, it's not clear to you, you look through the slides, or feel free to send me email. Okay, and thank you very much. Bye bye.